Hi, Jarrell. How are you? Okay. Glad to know that you're doing well. Hope you're doing well with your job. Okay, so you can check out your lab 10. We'll go ahead and get you started pretty soon. A little light today. All right. So today we're going to do lab 10. And that's going to be on multi-threading. Oh, I went past that. So you can find the lab here. Now I'm going to demo in my VirtualBox Linux machine, but you can also run this on your IDE. It should be working on your IDE as well. So if you want to use your IDE with your system multi-core, you can, or you can run it in VirtualBox, whichever is fine. Okay. So it doesn't have to be in the virtual machine, but the instructions and my demonstration is going to be in VirtualBox. And I'm using Ubuntu. So if you're using your virtual machine, it is good to make sure that you change your settings. So you can go into machine settings. Before you start, you need to change your system core. So here I give it 4 core and I'm giving it 4 gig of RAM just to make it a little bit more responsive. Now, the first part of our lab, we are going to write a single thread program. As we talked about single threaded program, where it would just be like one task after the next task, and then it's going to complete. So at the beginning for part A, it talks about how a thread is going to be executed as a sequence. And so it has instruction pointer that's going to track the context of what it is running. So you do see that we would need to make sure that the task continue, right? So here the simulation or the image that you see is that we have a task and then we have it pause for 1 second and it's going to pick up the next part of that task and then pause for 1 second and then it's going to complete. So what we can do is we can think about if it needs to be interrupted. In a single thread, we can have it preempted, meaning that it can be interrupted. It can probably, as we implement this, it can be put on hold. So we would do a sleep or a pause. And then we can have other threads that are also written to be ran, but in this case, we're only going to have one. Okay. So the technique that is explained here is going to be called yielding. We touched a little bit on this a while back, where we can pause it, right, and then have the other take care of the task. And so we would have yielding. Now, when you have one process and one thread, this is called the main thread. So when you're using a single process with one single thread, you're using a main thread. And so in all the single threaded program, you often see that it is just a main thread program. That's just another name for it. Now, when we're using the task function in our program, it's going to execute the thread. Then when we're using the sleep, we're going to pause it for 1 second and then we're going to execute the second time. So it's going to pick up after the pause and then it's going to pause again for 1 second. So there's 2 pauses or 2 delays or sleeps. And then after that, it's going to complete. So when you call the task function or the task function is called, the sleep function is then implemented after. Then the CPU won't do anything when it goes into sleep. Now, this is not efficient. It's just a way that we can show you can create a single thread. So once I logged into my virtual machine, and again, if you didn't catch it at the beginning, you can run these programs in your regular IDE. If you're using Linux, you can follow the exact instruction. But if you're using your IDE, you simply write the code and then run it, and then answer the questions, okay? For the Linux machine, once you're logged in, you're going to open up all apps, and then you can call on terminal. So just search for terminal. I'm going to go ahead and zoom in a little bit. Then we can begin using Nano to write our program. So then I would call on Nano single thread. I can't type today, .py. So here's my program, right? And then Alt-Shift 3 is going to give you the line number. So let's go through and talk about our program. So as we're using time, right? If you already have your time module, you don't have to do anything extra, but if you don't, you can add it. So we are going to have the pause. So we want to import in sleep from time module. And then we're going to use perf counter. This allows us to track as far as the performance counter for our clock. And then we have a function called task. So we have a task function, and then we're doing a print. So we say starting the task. We're going to pause it for 1 second, and we're going to print done. Now you are going to call the function the first time. So here is a function call. So as it called, because we define the pause inside the body of the function, it's gonna also call the sleep. So it's gonna execute print and then pause and then print done, right? And then it's gonna be called again. So the second time we're gonna call the function again, and within that it has to execute what's defined in the body. Now we did start the clock, so we did the start time variable, and that's going to be our performance counter. So we simply use the performance counter that's built in, and then we're going to end the clock timing. So our end time is here, and we want to subtract the start and the end time so we can get the amount of seconds that it used to execute the task, which is our function. So for the function call, the execution time is when we subtract the end time with the start time, and then we format it, right? So once I have my program written, which is only a few lines, then I'm going to hit Control X, right? Enter to save. Then I can execute the program in command line by using Python 3 and then the program name. So as the first task function is called, you would see that it prints starting task, and then it paused for 1 second, and then it print done. Then we call it again the second time. So sequentially, it's called twice. So it's going to go and print starting task, pause 1 second, and then done. So altogether, when it's called twice, right, when we subtract the difference in the start and the end time, we would have 2.0446 seconds, and that is roughly 2 seconds. It's a little bit over because it has to execute the other stuff. And I'm on 4-core on my virtual machine. So your time, if you're running it on more cores, right, or if your processor is faster, you would see a little bit different in the time output. So with this, we would see that it takes at least 2 seconds, right, for our task function to be called twice. It is a little bit over as it needs to do the other things like printing, starting task, and done. So after you have that written and ran, take a screen capture of your code and your output. Note your execution time. Now we want to use this as a base for us to evaluate when we add in the multi-thread. So throughout this lab, we're going to start with the single thread and then we would scale out. Any question with part A? Now, when you're running this on your IDE, you should be able to have the same output. Only difference is going to be your time might be a little bit better. Okay. So even if I assign 4 core to my virtual machine, remember that because we are single threaded, so that means that it is going to be one process, one task. Okay. So regardless, as we make it pause, it's still going to be required to the time note for us to wait. So I'm not really seeing a huge difference because the program is sequential when you're using single thread like this. Now, if you expand it a little further, as we look at part B, we can think about how we can manage the task with our multi-threads. So I will go ahead and proceed to part B. So now in part B, we are going to bring in threading module like what we've seen in the assignment. And we are going to implement multi-threads within a process. So here we are going to share memory location. So your data is going to come from one location. And that data, it belongs to the main thread. And it would be easier for the threads to communicate this way. So we want to make sure that we can set up the share location. Now you can, as we talked about in the lecture, you can have it communicate in separate process, in separate threads, but we want to make sure that we hit the objective of the program. So simply in this one, we're going to implement what's called lightweight processes. So threads are considered lightweight processes because they don't need a lot of memory location or allocation as we are sharing the data space. So they're not fully like regular processes where the addresses or the data is distributed. And so therefore we see that the program require less resources. It's considered to be cheaper than the multi-processing program. So in this program, you are going to have 3 threads. You're going to have a main thread that is created by the interpreter itself. And you are going to have 2 additional threads that's coded into the program. So when you add 2 threads by code, you are going to have a total of 3 because it's still going to have to execute your main thread. So it's going to look like this, where you have a task, and that task is going to go on pause for 1 second. While it goes on pause, the second task is going to pick up and start executing. Then the second task is going to go on pause for 1 second, and then it's going to finish and complete all the tasks. So in this particular exercise, it is a little bit more extended than your last program, as we're adding the object to represent our threads. So coming back to your terminal here, I'm going to go ahead and nano into my multi-thread program. And then let me turn on my Shift 3 for my line numbers, right? So let's look at the program detail. So we have the time import sleep like the last program and the perf counter for us to be able to track our time for execution. Then we are going to import in threading. So here you are going to use the thread superclass. So thread is going to be brought in. And with that, we're going to be able to access its thread superclass member functions, which is thread itself, right? Where we define your target. Then similar to the first part A, you are defining a function called task. We're going to print starting task, have it pause for 1 second, and then we're going to print done. We're going to start the clock. So your start time variable is going to hold the value for your performance count, perf counter, and that's going to activate the clock. Now, when you write the multi-threads, as we've seen in the lecture, you have to create the objects to represent your thread. So you have the first object and the second object. And you can call it anything you want. You can call it thread 1 or T1, thread 2 or T2. And this is a thread object. It's instantiated from the thread method from threading module. So therefore you have T1, and then you want to use thread, and inside its parameter, you want to put in your target as your function that you define. We've seen this before. Okay, so your target is always going to be whatever the function that you want to execute. So you would say target is task. And the same thing for T2, which is my thread 2. And so to start them both together, we're going to use the start function from threading module. So you're going to say T1, which is your object that you define, dot start. And T2 dot start. Then we want to make sure that the thread's complete before the main is executed. So we are going to make sure that we join them. So you are going to have T1.join and T2.join. Now, if you don't do this, we talked about this in the last few chapters, that you might have things that are going to take over, right? And not allowing the thread to complete. So we want to make sure that the thread's complete. So we would use join. Then I'm going to stop the clock. So I'm going to do end time with the perf counter. And then we're going to print the time difference. So I'm going to subtract the end time with the start time and format it and show that it's complete. So in this one, we don't call the task function at the end. We actually use it inside the parameter for the object and then use the start function to activate the task. Okay. So once I finish writing the program, I'm going to hit Control X and enter to save. And then I'm going to call on Python and run the file. So as you can see, we start both T1 and T2 at the same time, right? And they finish. They pause, of course, for 1 second each, and then they finish. So as both of them finish, then the last part's going to print, which is our time. So it took 1.0133 seconds. Now, unlike the other, when you're looking at the sequential program, we called task twice in part A, and it took 2 seconds, 2.04 seconds, a little bit over 2 seconds. Then in the second part, part B, because it is multi-thread, while the first task is done and it paused for 1 second, the second task pick up. So together, they both complete in 1.013 seconds based on my virtual machine. Okay, so here I can execute the same task with half of the time using multi-threads. So once we have that written and ran, take the screen capture of your code and output. Then we want to compare part B program to part A, the first and the second program. Now, looking back at the code, right, you can see that your threads start together at the same time. So they will launch at the same time and they will complete at the same time. Now, inside the function definition, we have them each pause for 1 second. What happens is that the first T1, when it paused, T2 is going to execute. So within that 1 second, both of the tasks can be completed. Whereas it didn't have to wait for the pause to be completed to start, to finish and then done, because as they both start together. Okay. Now in the first program, because it's sequential, you have one task that start and finish, and then the second task that start and then finish. So it has to wait for the first task to complete in order to start the second task in part A. Part B, while it waits for the first task, in the pause of the 1 second, the second task is completed. So we're able to shave off 50% in time for execution. Any question? This is a little bit longer than usual. I just want to make sure that you see the progression in how we use threads. Okay. All right. So now what we're going to see is we are going to work with arguments in the thread. And this gives you a little bit of practice, so it helps you kind of prepare on if you want to use thread for your project. So you can pass arguments to a function that is assigned to a thread. That's your target for your thread object. If you define your task function that accepts the argument, then you can create your threads as object to contain multiple threads. So in this case, we can also create threads list that contains a container that contains threads. And that will be executing concurrently, not sequentially, but to be able to overlap each other and execute. By using the join method, we can call it inside the loop, so that way it won't wait for all the threads to be completed before it executes your main thread. So that way, the program will wait for the first thread to complete before starting the next one, right? So we can control and coordinate using join. So in this one, the main difference with C and B is that you're going to see that we're going to have a thread container where we would have many threads. And we are going to use arguments that we're going to pass inside our function. So we are going to, in our terminal now, we're going to call our Python file thread arg. So here I'm going to type in thread arg as my .py after I use nano command. Okay, so let's look through the program together. We will look at how the program changed from the last part, which is part B. So we are going to use time for sleep, for pause, and then perp counter to track our time execution. And then we are going to have the threading. Let me turn on my caption. I forgot. Okay. So after I had my threading module, I'm going to then go ahead and define my function. So my function is going to call task. And I'm going to pass an argument, and this is a variable I'm passing that's going to be called ID. And that's going to be able to display the individual thread so I can see. Then I'm going to do a print inside the function body. And in this case, I'm going to use ID again. So it's going to show which task is starting. And then inside the definition of the function, I'm also going to have it pause for 1 second and then print done. Start the clock. Now, here is where your container comes in. Unlike the last program where we create individual threads as objects like T1 and T2, this one we're going to create a list of thread and we're going to make it 10 threads. Because it's many, we are going to loop. So we're going to use the for range. So you can say, you can use for I in, but this one we're going to use for n in range. And we're going to start at 1 and go until 11. So that's going to give us 10 threads. And for the loop, as we need to make each thread individual object, we're going to call it T. T is going to be holding that current thread as it loops. Okay, so it's an object that instantiated for the current thread. And the target again is going to be our task. And then for our args, we're just going to use arg is n. Make sure that you have the parentheses and the comma like this. And once it does that and it's creating the thread, what's going to do is going to append it to the list. So it's going to store it. And as it loops through from 1 through 10, your list is going to grow. So we're going to append T, and those are going to be our threads. So as it loops, we're going to start each thread. Now, since we have 10, we have to also do a loop for our join. So you're going to say for T in threads, and then you're going to have the join, T.join, because we define T there. So after we had joined each of the thread, right, it's going to wait for that to complete. We're going to stop the clock after it finished looping. And then lastly, we're going to print out the overall execution time. Okay, so once we wrote our program, we're going to go Control X to save, enter, and then we're going to run our program with Python. Thread r.py. So here, what it's going to do is going to loop through. So you are sequentially accessing and appending or creating and appending each of the thread, and then have it pause and print. Okay, print, pause, and print again. So we have thread 1 through 10, right? It stops after that for the start. So we started the 10th thread. Then it's going to go through and it's going to finish each one. And as it did that, we see that it is 1.033 seconds. Now, this is different than your first program, which is a sequential program, a single threaded program, in that we start, even though we loop through and started all 10, we actually start all 10 together. And as each one of them pause, the other one complete. So it's able to achieve that in 1.0033 seconds. Now compare this to the two the T1 and T2, which is 2 threads, right? We're roughly about pretty close. It's actually take less time to loop through. Okay. So we're able to accomplish 10 tasks with closely the same amount of time. So if you need to have multiple threads, consider using this technique where you create a list of your threads and then loop through to start them all. And as you do that, you append them to the storage location, which is your container of threads, and then be able to join them with a loop. And so you can see that they will be executed. Okay. And until all 10 is complete, then it's going to be able to execute the last line, which is the print, your main thread. Any question? So here we can see that it is different than the other programs where we're able to handle more threads using a list and arguments. And our argument simply is to show, the number of individual thread, the ID of it. So we are going to take the screen capture of the code and your output. And you need to explain how your argument, which is ID, how that's used in the program. So we use that in the function definition here. We pass it as a variable, right? That's going to store the individual thread identification or the number that represent that thread identification. And then later on, we are using it to print. And then here, when you create your thread object, your argument is going to represent the n, which is the number of that thread, which is ultimately the index of the thread list. Okay, so it treats each thread as an element, and it's going to use the index of that individual element as it loop through to display. And so that's how you would see it as the argument that's used in this program. Then you're going to explain how multi-threads are implemented to achieve a concurrency. So you should talk about how we created a list of thread, and as it treats the current thread as an object to execute the task, right? And then it gets added to the container. They all start at the same time, and they all have to finish before the main thread is complete by using join. So in this one, instead of, if we do it sequentially, that's going to take at least 10 seconds because we have it paused one for each, right? If we're creating 10 individual objects, that might be even slightly about the same time or even more. But if you're using loop and thread container, that is even improving your time in a much better sense. Okay, any question? Okay, so in part C, you saw that we are able to scale to 10 threads with a list and arguments. And so the output, this is what you would see. Any question? Okay, no question. Now what we're going to do is we are going to use thread for input and output. So you can see how it can generate files or edit files. In this one, instead of making files, I'm going to have it modify my files. Okay. So for IO bound tasks, it really depends on your time that would be set to generate the input and the output for the computation. So when we say IO bound task, this is going to be the time that's spent on IO, then on the computation. The CPU bound task is the time that's spent on the computation, which is significantly higher than the time that's waiting for IO. So when you're working with input and output, like writing things into storage, things like that for your input and output, if you're outputting it to a certain file, or if you're reading from a certain file, that could be also treated as IO. You have to think about how your IO bound task compared to your computation or your CPU bound task. The time that's spent on computation is going to be higher than the time that's spent on waiting for IO. So we would think about how we would use threading to optimize the IO bound task. Okay. And in real practice, we would see that it's used for remote resources like cloud servers, especially backing up data, modifying your data in groups, things like that, syncing data, especially on your database, reading and writing files. And also, if you think about like financial institution like banks, right? Things that we need to update and like transactions and things like that. All of those tend to be batch. That means that we would group a certain set of tasks or transactions and process them together instead of processing them individually, because that would save resources and time. So when you withdraw from your bank account, it doesn't take effect right away, right? You normally would have a period of time until the server processes that in batch. And that comes back to what you see with the IO bound task. So the database server needs to be able to sync, and then it's going to update the individual profile as it subtracts or add or modify the account information. And then it also, sync that information back to the web server, so that way you can see updates as you check your account via your web app. So in this exercise, we first need to create these 5 files, and you can do it in one command. Now, if you're using your IDE, right, just make sure that your Python file is in the same folder as this one, all of these files. So for example, if this is my folder for my assignment, I can just right click and I can just do new, and I would just create my text document, and you would have to manually do that for all 5 of them. test1.text, test2.txt, and so on. It has to be like there. And then my file, right, needs to be in the same location where I would run it. Now, if you're using the virtual machine, right, we can do it all in one shot. So you would do a touch command. Touch allows you to create files. So we can say test1.txt space, no comma, test2.txt, and so on. Okay, I already did this. So if I try to do it again, it's going to tell me that it's going to error out. It's going to say I already have the file, so I have to change up the name. Okay, so once you do the touch command as instructed on page 13 in Linux terminal, it's going to create these files for you. And then we can do an ls-l, that this is going to look at the file information. Or you can also do ls. So if I wanted to check to see if my file exists in Linux, I just simply do a list command or an ls. And so as you can see, I have these files, right? test1, test2, test3, test4, test5. Or if I do an ls-l and then an actual file name like test1.txt, it tells me the permission of the file, the user account that's accessing the file, and the user account that creates a file, and then the timestamp when that file was created. On the back end, it actually tracked like when that file was accessed, modified, and created, accessed, and modified. So that actually comes from the RAM area, but this is what you see from the storage location, which is the hard disk or the SSD. So these are the permissions of the file and the account associated with those permissions and the account created that, or the ownership account of that file. So once I have created using the touch command or manually created the file, just make sure that it's in the same location as my Python file. I'm going to go ahead and nano into my edit file.py. Okay, so let's look through our code now. All right, so we are using threading module, its superclass and methods. We are going to use the timer just like before. Here, the first function that we're going to have is called replace. Remember that I'm editing test 1, 2, 3, and 4, and 5. So I'm changing some file information. So I'm using the replace function, and I'm going to pass file name, substring, and new substring. And these are going to be the content text for my file. Then I want to print which file I'm processing. So just like what we did before with ID, right? In this case, our argument is file name. So we're going to pass that here, and then we're going to use that here as well to print. So we're going to say print processing file, and we're going to plug in like file 1, 2, 3, 4, 5. Then we're going to access the file and read it. So this is going to look at the content of your file. So like what we've seen in our lecture and the review at the beginning, we're going to use the with statement. We're going to say with open, and we're going to use file name. So we would open file 1, right? And then file 2, file 3, and so on. And R is going to be for our read. So we're going to read the file, and we're going to use it as F. And we are going to have a variable called content, or an object called content. And this is going to be storing whatever that's read. You would do this because if you don't, it's not going to be able to store what you read, especially on a larger file. So when it reads the text in the file, you want it to be able to store it inside a location where we can retrieve it. Okay, so the content is going to store what's read. Now what we're going to do is we're going to replace one group of text with another group of text. Okay, so we're going to update the content variable by calling the replace function. And as it reads it, it's going to take the substring and then change it, modify it to be the new substring. So we're going to replace substring with new substring. This is our new text. This is the old text that we are taking out. So it's going to update the variable here. And then after that, it's going to take what's updated and it's going to write it back to the file. So you have both input and output, to read and to write, which is output. So with that, we have another with statement, and we're going to use open, just like before, our file name, each of the file. And this time we're going to write SF. And we're going to write, and we're going to pass content, which is the updated. So it's going to take the new substring and plug it in and store it. Then we have a function called main, and our file names we're going to define in a list: test1, test2, test3, test4, and they're all text file, test5. Okay, so that's the IO part. Now it's going to be thread part. So we are going to create threads for file read and write. So we're going to have threads, and here's our thread container. It is a list, and we instantiate it using a thread, right, from threading module. Our target is the function that we define, which is replace, because we want to replace the content of all 5 files. Our arguments, just like the previous part, right? Instead of ID, we're going to put in file name, ID, and IDS. And these are the components of your file, because we would say file name and then file 1, file 2, file 3, and so on. And then we would include the for loop within, so that way we don't have to write it as a separate line. So we would say for file name and file names. Okay. And then we are going to start all our threads together. So just like the previous part, we're going to do the for loop. For thread in threads, we're going to do a thread.start. And then we are going to join them. So for thread and threads.join. So if you start, you should join. That's the two pieces always go together. Once you start, then you join. Then we are going to set up our main namespace now. So it says if our namespace is main, we're going to start the clock. We're going to call the main function, which was defined here. So we're going to call that here. We're going to end the clock, and then we're going to print the difference by subtracting n with the start, just like the other programs, so we can see the execution time. Okay, so once we write the program, we would save Control X and then enter to save. Then we're going to call on Python 3 to run, and then your file name. So it tells me that it's processing all of these, right? That is when you look at the print. That was coming from this because this function is called, so it shows that. Right, I started all the thread for all my 5 files together. So it started, and then they join, and then they all complete until the last one finished. Not necessarily the 5th one, but you know, all of them finished. Then it's going to print the last part, which is my time. So for my 5 files on a 4 core, I have about 0.043 seconds to complete. Now, these files are pretty, because they're empty, don't have much in it, right? Even if you append a little text, it's going to be, you know, so there's not a lot of things that needs to be replaced. But in the case that if you want for it to search for a specific string, like For example, if I'm going to replace like apple with strawberry as strings, right, then it's going to take a little longer to look through. But the benefit of having multi-thread is while it's working on the other core can pick up and work on other files. Okay. When you setting up the threads in the container. So you can automate some things like this with IO, and that's convenient, especially for administration purposes, or batch purposes, like when we do them in groups. Okay. So here you can see that we have both input and output in reading the file, right? And we store it into our content, and then we use that, update it, and then write it back into the file. Now you can also specify like what kind of substring you want to modify, things like that from your file. In that, I feel like it's probably better to write a search mechanism to be able to look for the text, but this is a convenient way to do that, using threads to be able to modify your file quickly. So after we have ran the program, we want to screenshot the code and the output. Note our execution time that was shown in the display at the end here. And then you can state how multi-thread is implemented. And coming back here, right, you created your threads, your list of threads to be able to access each file. And so as it call on the replace function, the threads are used to modify the file by replacing the substring with new substring. And we have a total of 5 files. So any question on IO? So now you know how to be able to use this for input-output purposes, especially with files, right? And then applying that concept with other things. And files, a lot of the times, like we do it for like archival or storage purposes. But it seems to be faster with automation. And this is the nice thing about Python, is that you can use it for this area, especially from my perspective, IT, Python scripting is so important, because it helped lift up, like, opening up the file and manually doing it one by one. We can just have the system do it with like a short script. All right, so that would be for IO, which is part D. Now, in this chapter, we also touch on setting up queued tasks in Python. And I want to use this opportunity for you to be able to write one, so you know how to work with thread queues. All right, so because we're using queue, we're going to use queue module and also threading module. And that's going to allow us to create a queue of threads. And we're also going to implement a lock, like what we talked about in our lecture. So that way you don't want one thread to modify the other one's data. Okay. Okay, so in the terminal now, I'm going to go ahead and go into nano. And this is going to be threads la.py. Shift 3. So now we're going to look at the code. So once I have my nano up, I can write my file, or if you run it on your IDE, just make sure that you bring in Q because it's a module. Okay, so first, what we're going to do is after the import statement, we have the threading, the queue, and the time. We are going to create our lock. And this is a lock object. You can name it anything you want. Right, the book usually just call it lock or L. Or so here we're going to do a print lock. And this is going to lock thread. So it's going to use threading and the superclass method, which is lock. And then we're going to define a function called example job, and we're going to pass the argument. And here, this is going to be worker. We're going to make it sleep or pause for 0.5 of a second. Then we are going to use the with statement. So while it locks, we want to be able to show some kind of thread information. So with the print lock, so it's going to use this, which is the lock of our thread. We're going to print the current thread, and we talked about this in our lecture as well. So we want to show the executing thread dot name. And then we're going to state task as a text string, and then we're going to bring in the worker information. Then in the next part, as you read the comment, it says the threader pulls the worker from the queue and processes it. So now we got to set up our queue of threads. So here we are going to define a function called threader. And we're going to implement a while loop. While it is true, it is going to start, right? So remember that it's going to get, when you use the get, it's going to put the worker, pull the worker from the queue. So that means it's going to get the worker from the queue. So here you're going to do the queue.get, and that's going to be stored in worker. And we're going to later define queue, as you see in the later part of the code. Then we're going to call on the previous function that's defined, which is example job worker. So we're going to run it. Now here it tells you that this is going to run the example job with the available worker in queue, which is your thread. It's going to execute the current worker. Then after that, it's going to complete. So we would say task done. Okay. Now, because we're using queue, we got to define it as an object of queue. So you would say queue is, and this is the superclass from the queue library or the queue module. We're going to set up the number of threads. So here we are going to have it a for range loop for X in range, and this is going to be 10. So we have 10 threads. And just like the last program, we have to create your thread object, which is T. And this is a thread object. And the target is going to be the first function because that's going to be the task function. I'm sorry, the second function, which is threader. Okay, this is the threading part. So your target is threader. And here we're going to classify it as a daemon because what's going to happen is that we have to make it die. Okay. So after the main dies, it's going to go away. And this is like a thing that you can use that's already pre-created. So you don't have to remove it manually with code. So you simply say t.daemon, and that's going to be true. We're going to start our threads. So it's going to begin by using the start function t.start. Now you could have it loop like what we've done in the last one with the start, but we can just start them individually like this. Then we're going to activate the clock. Then what we're going to do is we're going to update the jobs to 20 because we have 10 threads. It doesn't mean that it's 10 jobs. We might want to have more workers. So we would have 20 jobs, right, for 10 threads. So there you would need to update your worker range. So here's where you would do a for range for worker in range, and here you would give it 20. And then you would do a queue put. So it would add it to the queue, the worker. Remember, we talked about how there would be two sides, right? One container that's going to be the thread, and the other container that's going to be the task. And so it's going to access by pulling the thread to set up the queue of your task. So it's going to access the other container for your queue, which is here. Now it's going to be your worker. And we want to join the thread because we started it a while back. Okay, so once we join all 10 workers and 20 tasks, so now what we're going to do is we are going to make sure that these are still the comments we're going to finish. So sequentially, 20 tasks is going to take 0.5 seconds each. And that will be 10 seconds if we run it sequentially. If we just manually loop it, like what we traditionally do, right, that's going to take 10 seconds. But if you're using task queue, what's going to happen is all 10 of them is going to access the 20 tasks. And at once simultaneously, you are going to be able to accomplish the task a lot quicker than 10 seconds. Okay, and that's the whole purpose, is to be able to set up your queue for your task and then your worker to be able to access it. So even if we evenly distributed the thread, you can say that one worker every 2 tasks, right? So with that alone, we would see that there is an improvement in time. But as we are using multiple core to handle multiple threads, we're going to be able to shave off a lot of time. So, and then last we would run the print for the execution time, which is the time that it takes, subtract the start. The end time minus the start. So it'll give you the time for execution. Okay, so let's save, Control X, enter, and then call in Python. And then I would use my file name, threads la.py. And so it is obvious when you look at the threader that's printed out, it is not sequential. Okay, even if you're starting your thread, right, what you see is I have thread 1 and it's gonna tackle task 0. I have thread 2 tackle task 1, thread 8 task 4. And so whichever thread is available, it's gonna do the task at hand. Okay, so thread 7, thread 6, 5, task 5, and so on. So this gives you a visual of how the tasks are being handled. Okay. And then if you notice with thread 1, once it completed task 0, because we need to handle multiple tasks, it's going to do task 10, right? And then, so some of the threads are gonna come back after it completes, gonna handle the next task. So 2 with thread 11. So if you track the thread and the task, you're gonna see that you're gonna have the same thread after it completes handle another task. And so by the end, right, you're able to accomplish all the tasks that's given. And so it would be about 1 second versus 10 seconds, right? If we loop it sequentially, it will take 10 seconds. But if we write the threads, it's able to do that more. So while one thread is working, the other one is working on other tasks and so on. So if you have more workers, right, you're able to accomplish more tasks. And even in the twice the amount of tasks of the worker, we would see that it is 1 second. A little bit over 1. All right. So screenshot for our lab submission, your code and your output. Put down your execution time. Explain how multi-thread is implemented in the program to achieve concurrency. So you need to talk about how you created a thread pool or your workers pool and be able to set up your task queue for your workers to access the task. Now, the lock is used, right? At the beginning in the description, we saw that how it explains the lock in the other one, but here you see the lock locks that resource for that thread while it's working, right? You don't want other threads to come in and access the same thing where it would not be able to allow the current thread to complete or modify the data for the current thread. So this is why the lock was implemented. Okay. So, and we simply create a lock or print lock object for that. So you just you just instantiate the object to be able to lock. All right. And then with that object, you're going to use it inside the function definition for your worker because you want to coordinate the worker. So here you would use it with the inside the with statement for the print. And then talk about the queue. So the queue, we use that to number 1, create a queue of your task. Okay. And with that, we would be able to set up the jobs for your worker here and with the join. So it has to complete all the tasks before it could terminate. And then once it terminates, then the main's going to run. Okay. So this is a way that you can see how queue can be implemented. And this is based on the scale that we see compared to the last program. This can definitely be implemented for concurrent programming in a much higher scale. So you can have hundreds of tasks, right? And a lot more threads to be able to handle with queue compared to, you can implement the list like the last example or the part D, but at the same time, this is more effective, especially if you have a lot of threads and a lot of tasks. So you would consider using queue or task queue. Okay, so the whole objective in this is I want to make sure that you know how to be able to write multi-threads. And, looking at that compared to multiprocessing, this tends to be the preference, I think. If you know how to implement it appropriately, it can be very effective for Python. Any question? Okay, so make sure we answer the questions after we provide the screenshot, even though there are more programs, right? And I put the code, you can, I wrote it so it's not a screenshot, so you can, in case you need to check, you can check in case you have syntax error. Okay. All right. Okay. No questions? Okay. Remember what I said? Try to work on a little bit of your project at a time, even if you set up pseudocode or start planning out your program, maybe a little bit each week, so that way you can accomplish your task by the end of the class. You don't want to wait until the end. So I already released the project for this class. Make sure that you go through and be able to work on your project. So it should be like after this module. Okay. So think about the program that you want to write. Go back and look at your lab exercise, your notes, and your assignments for the pieces that you've done throughout. There only may be a few more things that we would add that would contribute to the project, like patterns and be able to handle some exceptions. So we would, in the next few weeks, we're going to address those, and then we will do the lab accordingly, so that way you know how to write that. Okay. But a big chunk of it we already hit, which is multiprocessing and threading. Okay. Let's see. So I will conduct a final review. I want to say like maybe week 14 or 15. I'm going to try to give you 15 off, but we'll see how this class is going to be as far as content goes. But yeah, there will be time for us to be able to tackle like the final review in 1 week. Okay. So next week we are going to have a quiz. That's the second part of, so the last few weeks that we cover, we're going to be quizzed on that. We're going to come back to web development side a little bit. We're going to talk about HTTP requests and how to handle that, and then implemented some of the concept that you've learned so far as well with it. And then after that, we're going to come back to deal with GIL and multi-thread and parallel processing. So this is when we're going to talk about like live lock, deadlock, race conditions, all of that good stuff. And then we're going to go through and work on our patterns. Okay, so after the patterns, you should be good to go. If you have any question or concern, I'm going to try to pull stuff together, maybe put things on my GitHub and be able to share the source code information, or, if the student already shared on GitHub, let me pull their GitHub. It just got to take me a little bit to go through the prior class and pull out the projects that's done well, so you can see some example of it. Okay. So you can write security program, or you can write any kind of program that you wish to write. What I suggest is start with the simple concept. Don't make your program too complex, and then it's going to become more complex as you build it, because you're going to start thinking of adding all different components. So think of like a program that would need like parallel processing or like need concurrent programming and be able to write it. Okay, there's plenty of needs for that kind of thing. So, all right, let me stop sharing and stop recording.